Good morning, students. Today we shall discuss the complex field of momentum using second quantization, and thereby we can obtain the eigenvalue of the momentum in terms of number operators. In the previous videos, we have applied the modified Klein-Gardner relativistic field equation to obtain the expression for the energy of a complex field, and we could obtain the eigenvalue of the energy of the photon. Similarly, we derived the expression for the eigenvalue of the total charge of the scalar complex fields, which we started from the expression of the charge density earlier. In all the expressions, we use the field operators, which contain the field functions and the momentum density operator in terms of raising and lowering operators along with the plane wave equation. But in this video lecture, we are going to continue the same thing. We are going to quantize the eigenvalue of the momentum, which will be in terms of number operators. Here the momentum is considered as a whole field guided by the probability current density, and we are going to use the expressions of the field function and momentum density. Thus we can say that the Hamiltonian, momentum and the total charge operators can be expressed in terms of number operators, and they can be written as diagonal elements. So let us start the expression. We know that the field equation of the momentum is given by P equals minus integration d cube x times pi of x, the momentum operator, del phi of x, the grade of field function, plus the complex conjugate of pi, which is nothing but pi dagger of x, and del phi dagger of x. And as I said earlier, that we are going to use the field function. The field functions are given by equation 2 and 3. So one is the ordinary field function, another one is the complex conjugate of the field function, which is given by equation 3. 2 and 3, equation 2 and 3 already we have used. We have used earlier in the video lectures to compute the charge operators, the eigenvalue of the total charge operators, and the eigenvalue of the energy of the photon. So we used already the field functions. So those field functions only we have taken. And the annihilation and creation of the momentum density operators are given by equation 4 and 5. We have also used this one in complex fields, where we have quantized the Hamiltonian in order to obtain the quantized energies, and pi and pi dagger. We have used these two expressions. Now let us differentiate equation 2. So this is equation 2. We are going to differentiate. So when you are going to differentiate equation 2, we will get del phi exactly like this. See here. So you are going to differentiate this one with respect to x. So that will give me ik, and here also you have minus ik. I have pulled ik out, so that will give me equation 6. So your del phi of x is given by I divided by root v summation over k divided by root of 2 omega k ak plus e power ikx minus ak minus dagger e power minus I k dot x. So differentiating equation 3. So this is your equation 3. Equation 3 is given by this. Now just differentiate this equation. So equation 3 can be differentiated with respect to x. That will give me equation 7. Now we know the expression for your pi of x, del phi of x, pi dagger of x, and del phi dagger of x. So these are the expressions we need for computing the momentum, the momentum density. So we need to have all the expressions. Now we are going to substitute these expressions here in equation 1. So equation 1 is given by this equation, and just to substitute all the expressions, your pi, del phi, pi dagger, del phi dagger, we will get equation 8. So you look at the equation now, you have p vector, which is given by, so this is nothing but your momentum, which is given by, now is just the pi of x and del phi of x. So look at the expression, your pi of x is here, your pi of x is here, and del phi of x is here. We are going to multiply these two. When you are going to multiply these two, we will have 1 divided by root p multiplied by 1 divided by root p will give me 1 by see here 1 by v, and omega k, root of omega k divided by root 2 multiplied by k times k divided by root of 2 omega k. This omega k and this omega k will get cancelled. You have 1 by root 2 multiplied by 1 by root 2 will give me 2. So that can be combined with v, that will give me 1 by 2v. This minus sign already which is there in the expression of our equation 1, which is nothing but your momentum. So now we have 1 divided by minus 1 divided by 2v summation over k integration d cube x. So this is your pi of x and this is your del phi of x, and this is your pi dagger of x, and this must be your del phi dagger of x. So we have 4 expressions now. We are going to multiply. Now I can pull I here also we have I. So I squared I can pull out. Here also I can pull I squared out. So I squared is nothing but minus 1. So this minus and this minus will cancel, will give me plus. So in the next expression we have 1 by 2v summation over k integration d cube x, and this is your pi of x, and this expression will be your del phi of x, and this will be your pi dagger, and this must be your del phi dagger of x. Now we are going to multiply. So we can multiply this expression, the first term with the first term of the second term, and the second term with the first term, and second term with the second term of these equations. So that we are going to multiply these equations very easily. So let us multiply now. The first term with the first term, that will give me ak plus dagger, and you have e power minus ikx here, and multiplied by k, so k will become k prime, and k will become k prime as I said earlier. So k prime plus e power ikx. So this is our first term. So first term with the second term will give us minus sign ak plus dagger e power minus ikx. Then you have k prime ak minus dagger e power minus ikx, k prime x. So similarly we can get the other two terms also, and plus now we will have 4 terms here. So multiplying the first term with the first term, multiplying the first term with the second term, multiplying second term with the second term, and multiplying the second term with the second term, we will have the last 2 equations. So we can have this equation exactly, equation 10. Now we can combine e power minus ikx with e power ik prime x. We can combine these two. We can write in terms of e power I minus I k minus k prime. So equation 10 can be written in terms of exponential together. So we have ak plus dagger ak prime plus k prime e power minus I have pulled minus I out. So we have k minus k prime x, and similarly other terms also can be written. So we can combinedly we can write the exponential term, and we can write the equation as exactly 11. Now we are going to use the expression for your delta function. So 1 by v integration d tau e power I plus or minus k prime x, which is equal to 1 by v integration d tau e power minus I k plus or minus k prime x can be written as delta function of k plus or minus k prime, and k equals plus or minus k prime. So we are going to use this delta function in equation 11. So for example, you just take the first term. First term is your k equals plus k prime. See here, your delta k is nothing but k minus k prime. So k equals plus k prime. So when you are going to substitute, that term will be, when k equals k prime, the remaining term will be 1. So you have k, you have see here k minus k prime. So you have k equals k prime. So instead of k prime, you have to substitute k. So this first term becomes k ak plus dagger. Instead of k prime, this will become k. So ak plus, the remaining term will be 1. Okay. So similarly go for the second term. When you are going to go for the second term, this will become k equals minus k prime. So wherever you find k prime, that will be replaced by minus k. So minus, already one k prime is there, you are going to replace it minus k. So this minus and that minus it will become plus. So you have plus k plus dagger and multiplied by A. See, K prime will become, as I said, minus K. So minus K minus dagger. So second term becomes plus sign. And what is the third term? Third term also here, K equals minus K prime. So wherever you find K prime, that will be replaced by minus K. So that term also will become plus. And the next term also can be written as exactly like this. And remaining terms can be written as exactly equation 13. So equation 11 becomes 13 now. And I have written the same thing here as equation 14. And just take this term. Okay, 1, 2, 3, 4, 5, 6th term. 6th term and 7th term. You look at the second term and 1, 2, 3, 4, 5, 6th term. You just look at the second term and 6th term. Okay, second term, these two terms. And here it is AK plus dagger, here it is A minus K minus dagger. But here it is AK minus dagger, A minus K plus dagger. One minus sign varies. So in order to go with AB minus BA, in order to use commutator relation. So I have used the technique as when you are going to have K equals minus K. Just replace this as K equals minus K. Minus K plus K means the momentum of the particle. Minus K means the momentum of the antiparticle, which is moving in the opposite direction. So just to look at, consider the equation 5. When summation over K equals minus 2 to plus 2, AK equals, this AK can be expanded as A minus 2 plus A minus 1 plus A naught plus A1 plus A2. Suppose when you are going to substitute instead of AK, you are going to substitute A minus K. Then the summation can be expanded in terms of A2 plus A1 plus A0 plus A minus 1 plus A minus 2. You just consider these two equations for right hand side, they are equal. So left hand side must be equal. So when you are going to substitute K equals minus K, we can say that both are equal. So you just substitute here. You just substitute in this sixth term, you substitute K equals minus K. Okay, so minus K, so K becomes your minus K, see here minus K, and K becomes your minus K, and minus K becomes your plus K. Similarly, you can use the seventh term as minus K, A minus K plus AK minus, because when you are going to compare these two, second term and sixth term, and third term and seventh term, they are exactly resembles with the commutator relation AB minus BA, which is equal to A comma B. So that's the idea that we have replaced K equals minus K, that technique. So now I have written the same equation. You just combine the equation 2 and 6, you combine 3 and 7 and use the quantization rule satisfying the following computation rules. We will have these two terms. You just pull K out, so that will give me AB minus BA, that will give me A comma B. So the computation relation A comma B equals 0 using this. And similarly you can use this one, K, pull it out, and you can use AB minus BA, which is equal to 0 here. So second term and sixth term combined together will give me 0. Similarly third term and seventh term will combine to be, that also will become 0. Now take the first term. I can now pull K vector out. So I can pull K vector out and take the first term. I have written as it is. Go to the fourth term. Go to this term. This term can be written as AK minus dagger, which is equal to AK minus dagger, AK minus plus 1. So the fourth term can be written as exactly like this. And I have written the fifth term as it is, same thing. And the last term is, I have used this expression and I have replaced with AK plus dagger, AK plus 1. Now you combine the first term and this term, that will give me 2 times. You combine this term and this term, that will give me 2 times. Plus 1 and plus 1 will give me 2. So I have written exactly as it is like this. I am going to combine the first term and with this term, that will give me 2 times of AK plus dagger, AK plus, and I am going to combine this term and this term, that will give me 2 times of AK minus dagger, AK minus. 1 plus 1 will give me 2. So I have pulled 2 out. So I can pull these 2 out. So these 2 and these 2 will get cancelled. So that's a mistake here. So I can pull these 2 out. So 2 divided by 2 and 2 by 2, that will get cancelled. We have K times AK plus dagger, AK plus AK minus dagger, AK minus plus 1. So 1, 2 is missing here, and 2 by 2 that will get cancelled. In the next I have written correctly. So we have the momentum vector which is equal to summation over k vector, and this can be replaced with nk plus, and this can be replaced with nk minus, which are all number operators, and plus 1 as it is like this. So this is equation 20. Now the next I am going to have separately I can write summation over with the number operators and summation over k in terms of k. And look at the second term, summation over k vector. Here we are talking about, as I said earlier, the momentum of the particle as well the momentum of the antiparticle. And when you are going to use this technique, as I said, this is for the momentum of the particle and momentum of the antiparticle. Almost they are same as I said just now. So when you are going to sum over the momentum of the particle and antiparticle, if they are equal, and the second term will become 0. See, second term will become 0 because we are talking about k as well minus k. When you are going to combine, and this will become 0 because of negative direction with the momentum of the antiparticle, and the second term will become 0. The complete expression for your quantization of the momentum in the complex field is given by equation 22. So your p vector, which is equal to summation over k vector times your number operator, which are nothing but nk plus nk minus. So this is your eigenvalue of the quantization of the momentum. Already we have quantized the momentum, so this is the eigenvalue of the momentum in the complex field. So thus the Hamiltonian, the momentum and the total charge operators are expressed in terms of number operators. So we have written in terms of number operators, and also they are all diagonal elements. So only then we can have eigenvalues. So in this class we have quantized the momentum, and thereby we could obtain the eigenvalue of the